Let's look at power series for sine and cosine. Remember that sine differentiates to cosine, which differentiates to minus sine, which differentiates to minus cosine. For this argument, let's suppose we have some positive x. Now you can see, just looking at the graph, sine x is less than x. Alternatively, you could look at your circle this arc length is x, this height is sine x. So clearly dropping a perpendicular is the quickest route to the x-axis. It's going to be quicker than following the arc. Okay, so if we're given sine x is less than x, then the area underneath sine x is less than the area underneath x for a particular x value. Like if we set our x value here, then this shaded area is going to be less than this triangular area. So we can write that using integration by integrating sine t dt between 0 and x, area from 0 to x, is going to be less than the integral from 0 to x t dt. Notice my original x, I'm now using a temporary variable t, which will disappear once the integration is done, and I'm now integrating from 0 to some x, and for any x greater than 0 this inequality is going to hold. You can see just looking at the picture. So using the fundamental theorem of calculus, we know that sine integrates to minus cos. So we have minus cos t between x and 0 is less than what does t integrate to? T squared over 2 factorial between x and 0. And this is just minus cos of x minus cos of naught. Cos of naught is 1, so we've got plus 1 is less than x squared over 2 factorial. Moving this across to this side, moving this across to this side, we have 1 minus x squared over 2 factorial is less than cos of x. And this is going to be true for all x greater than 0. So let's keep going. we can repeatedly apply the same technique. Let's again integrate both sides. So let's put a little box around it and keep going. Integral 1 minus t squared over 2 factorial dt between 0 and x is less than integral of cos t between 0 and x. So here we have t minus t cubed over 3 factorial between x and 0. The 0 bound is going to be nothing, so we've just got x minus x cubed over 3 factorial is less than, what does cos integrate to? Sine differentiates to cos, so cos integrates to sine. And sine t between x and 0 is just sine x minus sine 0, which is just sine x minus 0. So we have a second result. Let's keep going. Integrate again. And we now have x squared over 2 factorial minus x to the 4 over 4 factorial minus 0 squared over 2 factorial minus 0 to the 4 over 4 factorial. So for the 0 case, this thing is always going to be 0. So this is why I'm just integrating by inspection. I'm not bothering to write anything more down. It's trivial. Is less than sine t integrates to minus cos t between x and 0, which is minus cos of x minus cos of 0. Cos of 0 is 1, so it's minus minus 1. So now if we move that cos x across there, and we move these two terms across there, we can now get, so we add cos x to both sides. This is a lower bound for cos x, and this is an upper bound for cos x. So we've now sandwiched cos x between 1 minus x squared over 2 factorial and 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So on a number line, if this is our cos x, then this would be an underestimate. This would be an overestimate. I suppose the first guess would be just 1, which is going to be an overestimate. So that's the first term, 1. This is throwing in the second term, which makes us go under. This is throwing in the third term, which makes us go over again. Clearly, we do this a couple more times, the next term is just going to be the same as this, but there's going to be a minus x to the 6 over 6 factorial, and so on. So we can write cos x as 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus ... It's simple to show this converges. If you like, you could switch all these minuses to pluses and use a similar argument we used for exp of x. So we showed earlier that exp of x converges. I'm writing down the left margin all of the results that we're using. So also we use the fact that x to the k over k factorial differentiates to x to the k minus 1 over k minus 1 factorial and integrates to x to the k plus 1 over k plus 1 factorial. Now simultaneously the same thing of jumping, alternating each side around sin x is happening with these equations. So we also get sin x equals x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus ... Now these may well remind you of our power series for exp x. And in fact, if you just substitute x with jx, where j is the square root of minus 1, so remember j squared plus 1 equals 0. J is an imaginary number, so that is now prerequisite for this as well. So what's exp of jx going to be? Well, 1 plus jx plus jx squared, which is j squared x squared, which j squared is minus 1, so it's minus 1 times x squared, so that's actually a minus. And then plus jx cubed over 3 factorial. Jx cubed is j cubed x cubed, which is j squared j x cubed, which is minus 1x cubed over 3 factorial. Sorry, minus 1j x cubed over 3 factorial. So we've got minus j x cubed over 3 factorial. Did that make sense? I had jx and I cubed it, is j cubed x cubed, and j cubed is just j squared j x cubed, which is minus 1 j x cubed. Yeah? Start with one multiplied by j and we get j, multiplied by j again we get minus 1, multiplied by j again we get minus j, multiplied by j again and we get 1. So this is multiplying by j. And we start to see it's no coincidence that this fourfold rotation happens with multiplication by j. It's basically a 90-degree rotation, counterclockwise. So now if we separate out the real and imaginary parts, we've got 1 minus x squared plus x to the 4, x squared over 2 factorial plus x to the 4 over 4 factorial minus dot 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 plus j times x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus dot dot dot. Which is just equal to cos x plus j sine x. And that was exp of jx. And that is a great result, so it definitely deserves a box around it. This is Euler's identity. Euler is the dude that discovered it. Another way to make sense of Euler's identity is just to notice that the slope of exp jx is what? What does exp jx differentiate to? Well, we use the chain rule, so it's jx dash exp dash of jx, which is just j exp jx which is just our original exp jx rotated by 90 degrees. And similarly, if you consider a particle moving around the unit circle, with position vector cos theta sine theta, What's the velocity of that particle? Which is equal to our position, but rotated by 90 degrees. And also note that S of 0 is 1 and exp of j dot 0 is just exp of 0, which is 1. Yeah? Put x equals 0 and all of these terms disappear, leaving you with 1. So we have exp j x differentiating to itself but rotated 90 degrees, and we also have our position S differentiating to itself rotated by 90 degrees. And we also have exp j dot 0 being 1 and S of at 0 having a position of 1, 0. Note that we're using a few things we haven't yet shown formally, for example, complex differentiation, which works exactly as you would expect it to work. So your f dash at z is f of z plus h minus f of z over h, limit as h tends to 0, where h is now a complex number. And if you like, you could verify that z to the k over k factorial does indeed differentiate to the same, but k minus 1. Note that this doesn't constitute a proof. It suggests that the two things are the same thing, but it's tricky to prove it. So consider this a motivating idea, a way of gaining intuition.